Hello, we're back again with another episode of Aerospace Engineering with Brian McNulty. Today we're going to be talking about some of the chemical reactions that go into a combusting gases inside of a rocket engine. We're also going to be talking about thermal expansion, the rigidity of rocket nozzles, and fluid flow. Without further introduction, let's get started. To begin, we're just going to look at a basic rocket engine design that uses liquid hydrogen and liquid oxygen as an oxidizer, plus a spark plug to create water vapor and some excess heat. This is important. This is called a non-hypergolic process because it requires an external source of heat, which is the spark plug, to get the reaction going, since the reaction chemically doesn't just start igniting on its own. We'll talk about hypergolic processes in a moment. So, doing some internet research, I found that the Space Shuttle main engine, during its launch, will burn up to 500,000 kilograms of diatomic oxygen molecules. That's a lot of fuel. That's an extreme amount of fuel. And so in order to start doing our calculations, we'll have to do a kilogram to mole conversion. This is just basic chemistry stuff, but I'll go through it anyway. Here it is. Okay, so here you can see the chemical reaction at the top that I showed in the earlier in the video. Basically, 2 parts diatomic hydrogen liquid and 1 part diatomic oxygen liquid plus an ignition spark will yield these results. So to get started, the mole calculation, converting into moles, I said that the space shuttle burns 500,000 kilograms of liquid oxygen upon launch. We simply divide that by its molar mass, and what we get is this huge number right here, which is how many moles of O2 are burned. This is important to put it in moles because this will allow us to calculate the amount of heat that it generates, burning that much fuel. Now down here, I've actually calculated the heat, which is delta H. And so we basically take the number of moles that we calculated in the above step, and from some chemistry table, we know that 473.6 kilojoules of heat are produced from each 1 mole of diatomic oxygen burned. This yields a whopping 7.4 terajoules of heat energy released from this exothermic reaction. So that reaction is what's known as a non-hypergolic reaction in rocket engine design. Basically what it means is that it needed an external heat source, which is otherwise known as the spark plug. Now, when we've all seen the rocket launches on live TV or on Facebook, and they have kind of a camera beneath the diverging rocket nozzle that you see out of the back of the rocket, you see a lot of sparks, but that's actually the spark shower. That is not to be confused with the spark plug inside of the combustion chamber. This spark shower that you see outside of the rocket on the launch pad is basically there to keep any volatile chemicals from igniting because they pool up, if that weren't the case. So what this does is it basically just ignites any excess propellant that might be pooling up on the launch pad. Now, so that was a non-hypergolic reaction. Now I'm just going to mention real quick a hypergolic reaction in which the chemical reaction requires no spark plug. The chemical reaction is so volatile that just when the chemicals start mixing on their own, they will just start burning right away. Let's take a look quickly at an example of that. So here in black, this chemical reaction is monomethyl hydrazine mixed with nitrogen tetroxide. That yields products. I'm not going to go into balancing the chemical equation. This is not chemistry. But as you can see, this is going to be an example of a hypergolic reaction. Rocket engine designs with this type of system are much simpler, simply as you can imagine, because they don't require a spark, and you can control the flow of these chemicals with two control valves, two flow control valves, and that just kind of simplifies everything greatly for the rocket designers. So it's worth mentioning that hypergolic systems have a much lower ISP than non-hypergolic ones, and this makes sense considering the spacecraft that they're used, or the aircraft that they're used in, which include orbiting satellites, manned spacecraft, military aircraft, and other things of that nature. These engines are typically smaller than the non-hypergolic ones, and so you kind of would just expect those space missions to have a lower ISP, since they're not actually operating in Earth's gravity and trying to launch a massive object under the influence of it. So now that we've talked about hypergolic and non-hypergolic systems and some of the basic chemical reactions that occur within the combustion chamber of the rocket engine, we're now going to actually start talking about the rocket nozzle and its purpose and some of the phenomena that occur when dealing with these mechanisms. All right, so there's four components of the rocket nozzle system that I'm going to discuss right now. The first one is going to be the combustion chamber, where the gases are superheated and therefore pressurized inside the combustion chamber. The second component I'm going to talk about is what's called the converging rocket nozzle. This is the part of the rocket nozzle that you don't see when you from outside the spacecraft. You don't see it when you watch these space launches. Then we're going to talk about the nozzle throat, and we'll find that there's some design parameters that we need to follow carefully if we're going to have an effective rocket nozzle. And finally, the fourth component is going to be the diverging rocket nozzle, which is the part of the nozzle that you do see when you watch the space shuttle launches. All right, and as you see, I have drawn a crude diagram representing these four components, including the unused fuel and the unused oxidizer, along with these fuel lines feeding into the combustion chamber. So in the combustion chamber, you have potential chemical energy as the fuel and oxidizer are now mixed in the chamber. Now I put ignition energy because if you remember, I mentioned a spark plug. That spark plug is necessary because right now we're dealing with a non-hypergolic process. So one thing I really thought was cool was we moved down to this converging rocket nozzle. An important phenomenon in fluid flow, and I thought this was really interesting, is that subsonic fluids will always accelerate in a converging nozzle until they reach the speed of sound, or Mach 1, at the nozzle throat. And then something even more interesting happens here. Above the speed of sound, as these fluids are flowing at supersonic speeds, they will again continue accelerating through supersonic velocities out of the diverging nozzle. You can see why this is useful, as you have to lift the entire mass of a rocket using these chemical reactions and accelerating this exhaust velocity as the fluids flow towards the bottom of this diagram is going to be extremely useful. Okay, so that whole converging, diverging nozzle business, subsonic fluid velocity, supersonic fluid velocity, was quite verbose. So I thought I would offer an analogy, if you will, to better remember this phenomenon. So think about a garden hose. before you attach a nozzle to the end of your garden hose, the water flow is going quite slowly. And the water flow is obviously subsonic. It would be ridiculous if it was supersonic. Watering your garden with supersonic flowing liquids, that doesn't make sense. So the water flow is subsonic, and when you attach the converging nozzle to it, it accelerates. That's all you need to remember. The only difference is the velocity of the fluid as it exceeds the speed of sound or becomes supersonic. Fortunately for most of us, we don't water our gardens with supersonic flowing fluids, and therefore this analogy is quite helpful in that regard. Alright, so now I'm going to go back into the combustion chamber and kind of talk about what's happening in there, the physics behind why there's pressure buildup and things like that. Has a lot to do with the ideal gas law, which we all learn in physics and chemistry. Let's check it out. Here I've written the ideal gas law equation. P is for pressure, and then in green I've written all of the other parameters here, or the other variables. And so we have rho equals density. This R sub U is the universal gas constant, not to be confused with the specific gas constant. The specific gas constant is, as you can see from the equation, just the universal gas constant divided by the gas's molecular mass. Now, since these are gases, the density isn't really going to play a role because the density never gets very high with gases. As you know, that a liquid has a higher density than a gas, and a solid has a higher density than a liquid. So that's not to be concerned with. But the main factor in this is the temperature, which is T. And so T is going to influence the pressure the most out of all of these variables. I mentioned in an earlier video that pressure is always going to flow from greater pressure to least pressure just because of equilibrium things in the universe. And so basically when the gas is combusted in the combustion chamber, pressure is therefore built up, and that gas that is under great pressure due to its high temperature from the ignition in the combustion chamber is guided through the converging nozzle to the speed of sound until it reaches the throat, where it is exactly the speed of sound, and then the diverging nozzle, where it continues to accelerate even at supersonic velocities. For this whole pressure thing to all work out, this combustion chamber, as well as the nozzles, need to be a rigid structure. However, there are limits to this, because the more rigid you make a structure, the more massive it becomes. And you can imagine why this is a problem if you are trying to eliminate mass from the rocket that you are launching out of the Earth's gravitational field. So essentially, if the walls of the combustion chamber and the nozzles are rigid, we can maximize our pressure by increasing the temperature. When I say rigid, I mean that they do not expand. So the gas being heated in the combustion chamber is absolutely confined to the volume of the rocket engine design. Alright, so some other useful properties to know about this superheated gas flow is that this process is going to be adiabatic, meaning that heat transfer cannot take place into or out of these gases once they are heated. Another property of this is that they are reversible. This means that through the diverging rocket nozzle, if the gas are flowing in the opposite direction, in the reverse direction, through the diverging nozzle, which has now become the converging nozzle, these gases will decelerate if they are at supersonic velocities. Now, the same is true for the converging nozzle, which has now become the diverging nozzle. If they are at subsonic velocities, they will decelerate through that nozzle in the reverse flow. Now, by definition, if a process is adiabatic and reversible, this is known as an isentropic process. Alright, so that's going to wrap up our video for today. We talked about some basic chemical reactions, both hypergolic and non-hypergolic, and what those mean. We talked about the 4 different components of the rocket nozzle, which are going to be the combustion chamber, the converging rocket nozzle, the throat of the nozzle, and the diverging rocket nozzle, as well as the fluid velocities through those different components. And then we also talked about the pressure within the combustion chamber and the ideal gas law that governs that phenomenon. So if you liked the video, please like and subscribe below, and I'll see you next time on Aerospace Engineering with Brian McNulty.